Thank you very much. Thank you for the organizers for giving me one more opportunity to return to this wonderful institute. My second or third time. I can see I was here for the first time. You can see my picture 2 or 3 decades ago. I should update that picture, by the way. But okay, so that was a challenge because I'm more analyst than geometer. But I'm also concerned with mathematical physics, with some physical motivation. So when I got the invitation to come here, I had to see among the things I know, and I could tell you, which can be a little bit some challenge for you, I hope, at least in 2 points, is the topic of my talk today. So the geometrical motivation are the minimal and capillary surface in nonparametric form, okay? Which of course is a special case, a physical application that I shall try to see if it's useful or not. As you know, it's a very, very classical mathematical geometrical problem. In fact, you may remember that the Plato problem was the subject of the first field medals in the 30s of the last century. It was something really very, very deep and very classical in mathematics. My talk has nothing to do with that, except, sorry, the pointer. I pointed. Which one is this one? Oh, it's this one. Thank you. Yeah, except this very familiar minimal surface operator. And of course, my approach is coming from PDE. So basically, this is the main topic at my approach. And in fact, it is actually the variational approach, not the classical approach to the minimal surface operator, which of course may take into account some, well, the usual Lagrange multiplier for volume constraint or the constant curvature, sometimes also make appear some constant parameter here, or the so-called capillary term, taking the linear case with the constant capillary constant. Basically, this is the main motivation, because I will deal with more general quasi-linear operators. But in any case, the 2 new ideas that I bring here is to join to this equation this constraint, which I call here the bounded slope constraint, which is a physical challenge in a certain sense, because except probably the soap bubbles that you know that they blow up when they have the singular situation, they blow up, and we are very happy because that means the singularity arises, so no more solutions afterwards. However, in physics, in some membrane problems, they are not so thin, so there are some finite energy in the deformations or in the physical phenomena. So blow-up cannot physically appear. So what is the mathematical model to control that? I don't know the answer. I don't know if the physicists know the answer. But nevertheless, one possible is to impose this constraint. Mathematically, why not? The issue is what this constraint means. And we shall see mathematically that will introduce another Lagrange multiplier, which corresponds possibly physically to some force, which has some geometrical nature. And of course, now it requires some mathematical physical modeling to understand if this is good or not as a constraint. So this is the first idea that I wanted to bring you here, and it's more a challenge than a new idea, because it's a classical idea that you see in different physical models, the elastoclassical torsion. A second idea, which is probably also very controversial. Yesterday I asked you the question. I do not know the answer, so I also ask you all this question. If we take, for instance, the case of grain boundaries, rough boundaries, we know that, of course, curvature and the slopes are local properties. But if you take grain boundaries, if you take rough boundaries, what means the slope? How do you compute the slope? How do you approximate the slope? Is the fractional derivative a good tool? Well, probably, you see, I was a few years ago in a workshop about wildfires. And you know, wildfires bring these fires from the wind from distance very, very quickly. And so the levee flights are appropriate there. I was asking a physicist if that was a good model to these diffusion models for the propagation of wildfires. And he did some numerical computations, but apparently they were not so good. But on the other hand, you see, the fractional derivatives have been used in physics for many of the problems. And for a long time, I was not very much interested in fractional gradients, fractional derivatives, until Arbier until was in Lisbon giving a talk. And that day of his talk, he received a letter from the Geophysical American Society where his paper was accepted, and was doing some numerical computations with the nonlocal Helmholtz equation. And numerical approximations were for the fractional Laplacian were much more adequate to the physical observations than the usual Laplacian. That day, I became convinced that maybe the fractional derivatives may be useful. If they are useful here for the grain boundaries, the rough boundaries with these geometrical properties, I do not know, but this is the second challenge I leave you here today. Now let's do a little bit of mathematics and to see how this challenge can be mathematically interesting. Okay, now I go back to a different problem. So a linear operator for Laplacian, and this is a very classical, one of the first free-boundary problems that were considered in the 70s of last century. And in fact, this model corresponds to use the classical elastoplasticity theory with von Mises criteria for if you have a cylindrical bar that you are twisting and you have some kind of equilibrium, you just take what happens with the cross-section because basically it is cylindrical geometry, the cylindrical bar. Basically introduce the stress function, this kind of potential of the stress, because it depends only two variables, x1 and the planar, x1 and x2, and you have a kind of Poisson equation in the pure elastic regime in omega, and you have, I mean, it's up to a constant, so you just take 0 on the boundary. So this is basically, as you know, the criteria of the Euler equation of this quadratic Dirichlet integral with this linear term corresponding to this twisting angle, and this is a positive. These are elastic positive constants too. And then basically, what is von Mises criteria? Von Mises criteria is the fact that you are in elastical regime until this gradient of the stress function is below some threshold. Then you are in elastic regime, but if you cannot overpass this threshold, and if you attain it, you get the plastic one. This is a minimization problem as well, but now in a convex set of this type. So this is usual Sobolev space. And basically, the free boundary here is interesting for this T-shaped section because it puts you in evidence that in these corners, I mean these concave corners, there exists always a plastic region, as well as it starts to develop the plastic region from these longer domains. Can be just flat. So you see that this is well understood. This is even, I mean, the mathematical analysis of this problem is quite developed in last century, actually. But you see the free boundary here between the plastic and the elastic. And the free boundary arises because exactly this constraint, the gradient constraint, when the threshold is attained. Well, okay, this is the linear operator. So in all sources, when you linearize, you get Laplacian, basically, okay? So we could expect that, in fact, if you take this minimal surface operator, which of course is much more complicated even from the PD point of view, because it is a quasi-linear generated, because when the gradient goes to plus infinity, the elliptic constant generates to 0. You see that in that case, the situation is much more complex, but you can also imagine that this free boundary for these capillary surfaces with bounded slopes could make arise some free boundary of this type. And of course, here in these plastic, so-called plastic zones, we call it by abuse of language, that corresponds to some extra forces that should be imposed in order to avoid the blow-up of the gradient. Okay? Of course, the physical meaning of this is to be discussed. If the model is good or not is another matter. Okay, basically, this in particular, this minimization of these convex functionals in these convex sets basically are equivalent to the Euler inequality corresponding to what are called variation equalities also since the 60s, related to the obstacle problem that were also in these formulations are well known. So this is just to give you motivation and to give an intuition of what we could expect with these bounded slopes. Now let's come back. Now, okay, one more thing is that exactly what means this Lagrange multiplier was telling you. In fact, we have this constraint. Now suppose that the constant is normalized by 1. U is this function which has this bounded gradient constraint. And basically what happens is that this Lagrange multiplier, lambda tilde, in fact, Rodrigues in 72 was the first to prove that for general, I mean, two-dimensional domains, this Lagrange multiplier was bounded. It was even continuous if the domain was convex. But in any case, it was a function. And of course, the solution is Lipschitz. And the solution satisfies this kind of what I call the Lagrange multiplier problem because you can put it in this form. And in fact, you see that Lagrange, this lambda, or lambda tilde, is strictly positive only if the gradient threshold is attained. Because if this is positive, this must be 0 because you have this complementary condition to these two. Of course, you make this translation, you just normalize by 0, which will be done in the remaining part of this talk. So this is the corresponding, in this case, it is equivalent, this problem is equivalent. And of course, there is uniqueness of U, but a priori, it's not, there is no uniqueness of lambda tilde. This is because this is basically an element in the maximal Norton graph corresponding to this constraint. Okay, this is, in this case, an equivalent problem, but in general, it's not so. Why? Because the difficulty here, let's go back to the, now we can go directly to variation equality, to the minimal surface operator, so it becomes quasi-linear with this nonlinear term. And you can put all the terms here. I mean, this is the capillary, I mean, linear or nonlinear, can be even nonlinear. And you can hear some given function, which can be given by some other physical phenomena. For simplicity, you see, and the convex set now I write in this form. Okay? I use also this notation for D, for the gradient, and you see why. When I go to the fractional gradient, I prefer to use the delta, the D, not nabla. And the slope may be a constant or maybe a given function, but a bounded function, strictly positive, but a bounded function. And you see, this convex is in, these functions are Lipschitz functions. In particular, they are always Euler continuous. And we can consider, in fact, this as a special, I mean, the minimal surface operator as a special case of a quasi-linear operator, which is locally coercive. I mean, it's locally coercive means this property. With this positive constant may depend on R. R is, of course, some value that when it goes to plus infinity, of course, this coefficient goes to 0 as 1 over R2, basically. But this is, it becomes within this convex set, if this is bounded, this is automatically not only locally, it is locally, but this is contained in some ball of W infinity. So this means that basically with this constraint with R sufficiently large, larger than this one, for instance, we have that in fact it is uniformly coercive in this convex set, which is very good. Because in fact, this is a bounded convex set. So for the existence, with this constraint, this is not a deal. Even with this function f, depending on u, depending continuous on u, in any way, because this operator with this A and this H just continuous, this becomes essentially a pseudo-monotone operator, and this is a bounded convex set. So for the existence, there is always at least one solution. Of course, if you want to have uniqueness, a few, okay, this is strictly coercive, this is okay, but this one, if it's monotone, or even if it's one side Lipschitz continuous is a small constant below that is controlled by the Poincaré constant of the in H1 0, so there is still uniqueness of solution. So you can take nonlinear functions here, but in any case, since these are always a priori bounded functions, I just take an F because this does not really play an important role. The important role here is played by this quasi-linear operator, which can be the minimal surface operator or more generally any operator with this type of, something is, yeah, something missing is here. There's a misprint here, nevertheless. I found some misprints and I tried to correct them. Okay, now, with this variation equality, what can we do? We can also, we can also consider the corresponding, now with this already with quasi-linear notations, we can now consider the what I call the Lagrange multiplier problem. But here the situation is much more complicated because in the linear case of the Laplacian torsion, we had a priori that the lambda, the Lagrange multiplier, was a function, even an L-infinity function in that special case that Rodrigues studied. In fact, in more general situations, we do not have the regularity of this Lagrange multiplier lambda. In fact, that's why we formulate this. In fact, this was an idea that my co-author Lisa Santos should have said that part of these results are co-authored by some co-authors, Lisa Santos and my PhD student Pedro Campos, and also partially with the SIS. But in fact, in general, we replace this integral term, which is in variational form. This is L infinity function. There is no problem. In fact, it could be just L1 because this is L infinity. This is L infinity. But in fact, is that in general we do not obtain that irregularity. And the idea is basically to introduce the dual space of L infinity, which is not very comfortable. Mathematicians try to avoid dual of L infinity because it's non-separable. When applied the Banach-Lauglut theorem, you do not deal with sequence, you deal with generalized sequence or nets. Numerically, it's a mess. I don't know if there is any way to make approximation in the dual of L infinity. Okay, so, but mathematically it makes sense. This is a nice object in some big Banach space, but it exists and has some nice mathematical properties. In particular, in fact, for any element in the dual of L infinity, you can associate it with a finite additive measure through this representation, okay, for any L infinity function. Of course, the finite additive measure bound to total variation, absolute continuous spectral Lebesgue measure, and you see, you just construct the random integral, so this is a mathematical, very respectable object. Of course, very difficult to make approximations, but it is a mathematical object with what you can define an order in the dual sense, okay, taking non-negative test function, say. So you can still call this a variational approximation. And of course, here you have vector fields. So this is a vector duality, which for L infinity gradients, you can write as a scalar one, okay? So this is notation that we are going to use. And so the generalized expression in variational or duality form of the Lagrange multiplier problem associated with this gradient constraint is this one. So, okay, is there a solution? Yes, we'll see, but we'll see this in the more general framework of the fractional gradient. And the fractional gradient I want to consider is the distribution of his fractional gradient. Again, when you go into fractional world, it is a wild world because there are many definitions of fractional derivatives. You can take more than one. This one, I mean, the Ries fractional gradient has at least a big advantage, which is Basically, it is independent of direction, so you can make, which is important for the physical applications. It is well suited because it corresponds, in fact, if you apply the corresponding divergence, what is, by the way, what is the Riesz fractional gradient? Is the convolution of the Riesz kernel with the classical gradient, or the classical gradient of the convolution of the Riesz kernel with the function. Of course, this is for smooth enough functions, because the convolution involves the Riesz kernel, and the Riesz kernel is, of course, singular. And of course, the definition of this convolution can be done in this form, and you take just alpha to be 1 minus sigma. Sigma is, of course, the fractional parameter between 0 and 1. So one nice thing is that, of course, you can construct the classical, there exists for the classical fractional Laplacian at least 10 other definitions, and this is probably the 11th definition. Maybe there will be more. There are lots of definitions for the fractional Laplacian. They're all equivalent, of course, for smooth function at least. But in any case, this is nice. But it's also nice because this Riesz fractional gradient is distributional in one sense. And it is also convenient because you can take here some anisotropy or linear operators. There is another nice thing, is that when sigma goes to 1, the Riesz kernel, when alpha goes to 0, basically this convolution, this Riesz kernel converts in a certain sense to the identity operator. So you see that if alpha goes to 0, basically here this goes to 1, and basically this goes for smooth functions in some LP spaces, it goes to the classical gradient. So in a certain sense, this is a classical approach, an approximation of the local model. There are two bad things with this gradient. First is that it does not behave well with maximal principles. If you construct elliptic operators, it's not clear if there is any kind of maximal principles. But for energy type estimates, it's perfect. It's variational. You can work with the Sobolev type of spaces, okay, which are the classical for P equal to the classical Sobolev spaces. For P different from 2, they are what I call the Calderon spaces, are different from the Sobolev-Gallardo fractional space. But this is not true for today. So why I claim this is an approximation? I produce here a nice graph, a nice computation that my PhD student did. Pedro Campos, he did this, the one-dimensional fractional gradient and fractional derivative of this 10th function, which of course the classical derivative is a step function. You see that for small sigma, it is very, very rough. Okay? For sigma equal to 1/2, it becomes like this. But if sigma is almost 1, 99.99, you see it's almost the step function, which is the distributional derivative of the limit. So in a certain sense, when sigma goes to 1, this shows clearly, geometrically, that you approach the classical gradient. Okay, so maybe it is a good approximation of the local slope. Okay, now let's see what is the functional framework. I go very quickly. So since we are basically in the Bertium framework, we work with the usual Sobolev space, H sigma 0, but we work with this equivalent norm, with L2 norm of the Riesz gradient, the sigma Riesz gradient, or the Riesz sigma gradient. And there exists a Poincare Sobolev inequality. There exists even the Sobolev inclusions. So there is also the Relish-Kondrachov compactness embeddings. But basically, we are dealing with bounded fractional gradients. And in fact, we did with this subspace. And basically, these are still, for any sigma positive, all the continuous functions. Okay? For sigma equal to 1, basically, this is the classical gradient. And this is, of course, the Lipschitz function. So what is now our mathematical results. We formulate similarly. See that, in fact, this is in scalar duality between L infinity, the dual of L infinity, and L infinity, because the fractional gradient are bounded. So this is a scalar bounded function, and you have the quasi-linear operator, could be the minimal surface operator, of course, and they put everything in F because this makes no really importance. No. And of course, this is the duality or variational formulation in this framework. And of course, you have this for this gradient constraint, the slope constraint, which is now non-negative. So if it's 0, we may have, I mean, if the threshold is not attained, basically we have the equation, because if the term is not attained, lambda must be 0, so this does not happen. So we have basically the equation. If the threshold is, if the gradient, the slope is below the threshold, you have the equation. Otherwise, we have this extra term that represents a kind of extra force, which is very in a very wild space, but nevertheless, it's a mathematical object that represents something possible in some physical problems. Okay, so of course, this operator can be more general, can depend on x, and we use this notation for the scalar and for the vectorial duality. Of course, non-negativity means in duality sense. Okay, now what is the corresponding variational inequality problem? Is just taking the classical variational equality for this convex set in H sigma 0, which is a closed convex set, non-empty, of course. 0 is always there. And this is the classical, and of course, depending, of course, on this F, but if this is nice behavior, monotone behavior in a nice way with respect to U, there exists a unique solution to this problem. And in fact, what is relevant here is that it's just a remark that, in fact, if lambda U solves the Lagrange multiplier problem, then U solves the variation equality problem. And the reason is just very simple, is because if you combine these conditions in the duality, you see that you have that the extra term as the extra term here as the right sign. So from the equation you get the inequality. Okay, now I'm about to finish. What are the results? Of course, you can imagine that basically, to start with, you need to see if this is a well-posed problem in a certain sense. And indeed, we have the existence of solution for the Lagrange multiplier problem. So the existence of this pair with the Lagrange multiplier in the dual of L infinity, the U in this convex set, which is in this sub-F fractional space with bounded fractional gradient with respect to this G. And this U is unique, solving the variation equality, provided, of course, that elliptic constant of that quasi-linear operator is positive. Actually, it is possible to let this below go to 0, provided that we have an a priori bound for the ds, for the fractional gradient, which, of course, does not cover the fully unbounded slope, but with bounded slope, we can let this quasi-linear operator to be also generated. But this is a technical issue. And in this case, of course, you lose, in general, you lose the uniqueness of the solution of the variation equality itself if you are in this framework. But it's just, this is strictly monotone, this is just monotone. And because you are in a bounded convex set, there is extra solution. Okay. Now, you've seen by these graphs, and in fact, it can be proved analytically, that this fractional gradient approach the classical gradient when sigma goes to 1. In fact, what happens to the solution? In fact, it goes as we expect, we go, of course, there is one important thing here is that you notice that there is a difference between this formulation. Or this formulation is that the duality here is on ORD, while for the local problem is only in omega. Because I should have mentioned that before, that you see here it was with omega, because of course the functions are defined in omega. In general, always the least fractional gradient for a function which is even zero outside omega. You notice that I've reduced everything to the homogeneous Dirichlet boundary condition to avoid technical problems. The least fractional gradient is defined everywhere in Rn. Okay? So that's why in this formulation we need to have here this duality, while here is not important because these functions are zero outside omega. And this duality, of course, is in the duality in the sense of Rd. Okay. Now, in fact, we need to restrict this is always, because this is duality can be restricted to the L infinity function that vanish outside zero. That's what interests us, because in the limit case, as you expect, when sigma goes to 1, we have the conversion of the solutions, okay, in this weak space, but even strongly by some compactness. If you take a sigma smaller, for any, in fact, it is by compactness. It's even uniformly, and of course, these functions, both functions are zero outside omega. But in the limit formulation, we restrict here because, of course, also these functions are zero outside omega. This convergence takes place everywhere, but then we restrict these to these functions, and you just restrict this duality to omega, of course. And basically, this is the first limit problem, the limit theorem, as we expected. Of course, there is here a small trick, is that in this first version of this theorem, we require that this threshold is a little bit more, because in fact, if it's just a constant, for instance, does not belong here, but belongs basically here, the fact is that the Rodrigues gradient tends to zero very fast at infinity. So you can always replace the G constant by some G that goes to zero at infinity, and you still have basically the same, not the same convex, but you have the same solution, because the solution does not also tends to zero. The gradient of the fractional gradient of solution also tends to zero quite fast at infinity. In any case, this power gives you a kind of control of that value. Okay. Another thing is, in order to finish, my time is probably almost over, but for physical applications, sometimes if you want to control the gradient slope could depend on solution itself. And it becomes a much more complicated problem called, in variational framework, called quasi-variational equalities, in the sense that the threshold, I mean the convex as well, depends on the solution itself. So basically, the variational equality is making the convex set depending on the solution by some kind of operator. And of course, now you may play around with properties of this operator. And one important thing is that if you take a fixed slope here, there is a nice property that the L2 norm square of the fractional gradient, or the classical gradients, the gradients generally, depends as, well, if you just take, it's 1/2, but if you take this square root, you just take, it's not the same power, but this is enough to give a kind of strong continuous dependence if this operator behaves well in L infinity, in the space where the slopes are considered. So with this continuous dependence result, basically you can have different possibilities of choice of this operator, nonlinear operator. This is the L2 star for the HS embedding. Of course, it could be S more than one, could be S equal 1, which is local problem. Basically here, the theory is basically the same, just changing the Sobolev space HS. And in fact, one possible case is to use a kind of non-local operator with a composition with a continuous function. And in this case, you may have it's sufficient to say that this is continuous and a priori bounded. So this gives you basically, because a priori, if it is a priori bounded, this operator, Schauder fixed point arises without, it's a simple example. A more interesting example is that maybe you can make this depend on the gradient. Of course, making some kind of regularization, because you need some kind of compactness. But with this kind of regularization, you can also say that you can construct a completely continuous and bounded operator. So there exists a fixed point again by Schauder, and you can make an existence required solution, or else some other examples, just a continuous operator if you are directly in this space of slopes, say, and then you ask also. Okay, and this variational approach to this kind of models with possible application to these geometrical or mathematical physical problems. This is to be discussed, and this is a challenge that I leave you here, is the main topic of my talk today. Thank you for your attention.